In this video, we're going to have a look at how we can calculate the closest approach between two objects, or the closest distance that they will come to each other. Now, previously we've looked at the relative displacement to do this. We have tried to find the magnitude of our relative displacement of say, A from B, and using that magnitude or that scalar value, over time, plotted that to find the minimum of that function. So let's see this in action. Here's our first situation. At 6 a.m, ship A is position vector -4,2 and travels with velocity 3, -1 kilometers per hour. And at the same time, we've got ship B at 10, -4, and that's traveling at -1,2 kilometers per hour. What we want to do is find the closest distance between these ships and find at what time this occurs. So let's find the relative displacement of ship A from ship B over time. So what we need to define is the displacement of A. Well, that's going to be -4 plus 3t. So I'm just taking the I values from its position and velocity. And the J will be 2 take t. Subtract the displacement of B. So we're going to have 10 subtract t and -4 plus 2t. So A relative to B in terms of its movement over time will be -14 plus 4t as the I component and 6 take 3t for the J component. So that's how A is moving relative to B. So what we can do now is find the magnitude of this, which is going to be the square root of -14 plus 4t squared and 6 take 3t squared, added together and finding the square root to give us that scalar. But because we don't know at what time this occurs, we can plot this as a function over time, and then we can find its minimum. So we can either graph what this is going to look like and find that minimum point, or we can use function minimum in the main screen of our calculator, we can bring up function min and we simply put in that function. If we do that, we get a solution that says the minimum value, which is our magnitude of A relative to B, is 3.6 kilometers, so that's the distance, and it says t is 2.96, and that's in hours. So we could say the closest distance, or the closest approach of one to the other, is 3.6 kilometers apart, and that happens at 2.96 hours after, and in our question it was 6 a.m. So that will be 8 and 0.96 is 58 minutes of 8:58 a.m. There is actually an easier way that we can have a look at what the closest approach between two objects is using our scalar product. So that takes away the need to form the magnitude and solve it for its minimum. So using the scalar product, here's a reminder of what our scalar products are, depending on whether we've got component form or magnitudes and the angle between. We're going to have a look at another situation now that looks at the closest distance between a moving object, we're going to call that ship A, and a stationary object, ship B. So we've got ship A, which is positioned at 2:18, and it's travelling at 2, -3 kilometers an hour. So we can see that it's travelling in this direction. So let's see if we can draw that in. So we can see exactly the movement that it is making over time. Now we've got ship B that's anchored at 5:7. So there it is. So we've got the displacement of A over time. We could use those two bits of information, its position and velocity, to define its movement over time, or its position over time, as 2 plus 2t and 18 take 3t as its components. We've got the lovely direction of A travel. Now B is stationary, and what we can also put on here is the fact that the velocity of A moving is given as 2, -3. So that's shown in that lovely direction as it's going down. So what we're trying to do here is find when A and B are the closest. Well, if we have a look at all the opportunities from B where A can be noticed. So if we have a look at the displacement of A relative to B at certain times, we could look at it when A is at 8 AM and hasn't moved. And we can see it over various hours. But we can see that the closest that B is going to get to A is in fact when it is perpendicular. So let's call this point P. Its closest approach is when it is perpendicular to the movement of A. In fact, what we can do here is define the velocity of A as the velocity of A relative to B, because B isn't moving, so that the velocity of A relative to B is just the velocity of A. So they're closest when the velocity of A relative to B over time, which we've got here, is going to be perpendicular to what we could call PB. Now, if we think about how we define PB, well, this distance, PB, is just looking at the change in A's displacement relative to B. And when we know that we've got the scalar product and two things are perpendicular, the angle between them is 90 degrees. And going back to what we know about the scalar product, when we've got the angle between the vectors being 90 degrees, the cos of 90 is 0, which means we have want to know when the scalar product is equal to 0. And that's between the velocity and this displacement of A relative to B. So we can write that in a little bit of a nicer way. When we consider how A is changing its position relative to B, scalar product with the velocity of A relative to B, we want that always to equal 0. And this will tell us the closest value between those two vectors. So let's go back to our example and see if this actually works. So we've got our displacement of A up the top here that we've worked out. So we want that now relative to B. So we're going to slightly change this by now subtracting B, and the position of B is 5, 7. So we're going to have 2 take 5, so that's -3 plus 2t, and 18 take 7 is going to be 11 take 3t. So there we go, we've got our displacement of A relative to B or from B. So let's place that down here. We've got -3 plus 2t and 11 take 3t. We want to scalar product that with the velocity of A relative to B. Well, in our case, B isn't moving, so relative to B, A is just still moving with its standard velocity of 2, -3. So let's solve when this scalar product is 0. So remember, a scalar product is multiplying, so we're going to multiply our I components with our I component here. So we've got -3 times 2, which is -6. 2t times 2 is plus 4t. And then we're going to add on our scalar product of the j components. 11 times -33 is -33. And -3t times -3 is positive 9t. Solving out this, we've got 13t take 39 equals 0, so t will equal 3. So what we found here is after 3 hours of A moving, and A began moving at 8 a.m, so at 11 a.m, ship A and B will be closest. What we want to do now is work out where that will be. So the distance is going to be the magnitude of A relative to B, but instead of over time, we know we want it after 3 hours. So we can substitute 3 back into our displacement vector, and we get 3, 2. So the magnitude of that is going to be 3 squared plus 2 squared, which is the square root of 13, or 3.61 kilometres. So we can add that to our description. So after 3 hours at 11 a.m, ship A and B will be closest, only 3.61 kilometres apart. Okay, let's take a look at situation 1 again. Previously, when we used the function minimum, we found a solution of 3.6 kilometres at 8:58 a.m. So we want to see if we actually get that same solution using our new scalar product that we found, saying A relative to B over time, scalar product with the velocity of A relative to B equaling 0. So let's actually find a vector to represent these. So let's work out first of all our A relative to B vector. So this is going to be -4 plus 3t and 2 take t for the displacement of A, take the displacement of B over time. Now we have 2 ships moving, and we get -14 plus 4t and 6 take 3t, and we found that earlier. Let's work out the velocity of A relative to B. That's just going to be the velocity of A, 3 -1. Take the velocity of B, -1, 2, and we get 4 and -3. Okay, so let's work out the scalar product. So we've got -14 plus 4t, 6 take 3t, scalar product with 4, -3, and that must equal 0. So we end up with -56, so that's -14 times 4, plus 16t, take 18 plus 9t equals 0, -74 plus 25t equals 0, so t is 2.96 hours. Okay, so now we need to work out that distance, which is going to be A relative to B at 2.96 hours. So we need the magnitude of our solution. We've got -2.16 for the I component and -2.88 for the J. So when we find the magnitude of these, we end up with 3.6 kilometres exactly. So we can say the closest approach between ships A and B is at, now we've got 2.96 hours, so that's 8:58 a.m. And that will be at 3.6 kilometres apart. And that matches our solution when we use the function minimum. So now I'd like you to have a go at a question using that scalar product, where the displacement of A relative to B over time should be the same, equaling to the scalar product of the velocities of A relative to B should equal 0. Just to note that when we're looking at the displacement, that's over time multiplied by the vector of the velocities themselves. I'd like you to pause the video, have a go at this question, and come back and check your solution. Forming the A relative to B displacement over time and the velocity of A relative to B, we can find that scalar product to equal 0, which gives us t equals 3 hours. We can then substitute t equals 3 into our displacement vector for A relative to B to get 25.3 kilometres is the closest approach, happening 3 hours after 8 AM, hence at 11 AM.